Welcome to a new video in block 2 of TBMT42, Systems Biology, Digital Twins, and AI. So we are approaching the end of this block, which is also somehow the fruit of everything. We did the optimization and we did the uncertainty analysis and all of that. So now we need to draw conclusions. What can we actually learn from all of this stuff? And in this particular video, we will look at some statistical tests that can be applied to draw conclusions. And in particular, we will ask, is the agreement between the data and the simulation, is it good enough to serve as a valid explanation? So an explanation here is a hypothesis that both is statistically good enough and is also sort of interpretable in a good way. So is the explanation or hypothesis, if you want, is that good enough or not? And then the other question that we will ask and find statistical test for is if another model is significantly better. If you have two competing hypotheses. Okay, so let's have a look. So we have for the question of whether a model is good enough or not, we have the chi-square test, which looks at the size of the residuals. When we look at correlation, which is another problem, that the residuals might be correlated, then we look at some tests for that, just learn some of the names and very basic formulas. And then we look at model comparison tests. The likelihood ratio test is the one that we'll mention, but there are also other ones. Mentioned shortly again bootstrapping approaches, and finally something about the very important aspect of cross-validation and checking for overfitting. So chi-square, this chi-square test, this is maybe the most widely used test in systems biology, which is basically based on the very simple observation that if you have the y, the measurement data, and you have the y hat, if the difference between those two is given by an additive and normally distributed process, where the uncertainty, where this distribution has the standard deviation sigma, then if you divide by that sigma, since you already took away the mean, the only thing that remains of the distribution is a normal distribution with 0 mean and standard deviation 1. So this is an N01 distribution. So if you then just take many of those and you combine them with each other, then this is by definition a chi-square distribution. So a chi-square distribution is defined as the sum of squares of N01 distributions. So since all of these ones, which are the terms in a normal cost function, or the simplest version of the cost function, these should form an N01 distribution, and therefore the sum of all of those, or the sum of the squares of all of those, should follow a chi-square distribution, because that's what a chi-square distribution is. Based on that simple observation, we have a very useful test, which is that this test here, which is just a cost, if we don't have any modifications, we don't take the square, we don't divide by the number of data points, and so on. If that is bigger than the cumulative chi-square distribution and the inverse of that, with a 95% confidence or with a 95% cutoff, that means that it's unlikely that this assumption holds, meaning that it's unlikely that y minus y hat is just given by a normally distributed process with the standard deviation sigma. So it's probably bigger than that. So it's so if this is the measurement noise, it means that we can't describe everything but the noise. So the y minus y hat is too big. So if this is above this cutoff, then we should reject the model because you're not close enough to the data. So if it follows this distribution, then this is we can simply check if that's true or not. And if this is not fulfilled, that means that we are either in a rare case, 1 out of 20, where this happens at random, or you have problems with the data. And if you want to have more than 1 out of 20, you replace this by 0.99 and so on. And the other thing that you can replace here is the degrees of freedom. And that requires some elaboration. So the sort of least conservative approach is to just use the number of data points because you assume that everything is independent. But if you have fitted the model to the data that you're using this test for, then you should really account for that. So then you should really say that, okay, for each parameter that I fitted, I should take away one term in this. But if the parameters are not identifiable, they will not be independent. So therefore, maybe you shouldn't take all of the parameters. Then maybe you should use just a number of identifiable parameters that you compensate for. So the question is, how many identifiable parameters do you have? Yeah, and that depends on where you put the cutoff of what is identifiable and not. So you see here that there is sort of a scale ranging from basically the degrees of freedom equal the number of data points to degrees of freedom equals number of data points minus the number of parameters, and probably the truth is somewhere in between. So this means that you sort of have a judgment call within this range. And you should always combine these type of statistical tests with your own judgment, with your own sort of assessment, just looking at the agreement. Is this good enough? Are you happy enough with this agreement? That's always the bottom line. Statistical test is just a way to support that argument. So you shouldn't be too concerned with this sort of ambiguity in number of degrees of freedom. Because you should never only rely on a statistical test. You should always bring your own judgment. But you have this sort of ambiguity here. So this is why you might also want to use other approaches. So here we have the problem that the residuals are too big. The simulation is here, and never are you within the standard deviation of the measurement noise. So this would be rejected by a chi-square test for sure. So you don't always have to be within one standard deviation. In fact, even if you have the true model, so the true model generated the data, maybe some 30% of the times it will be outside. But you shouldn't be outside this this often. So this would be rejected by a chi-square test. So here you have the problem that the residuals are too big. But you might also have another problem, which is that the residuals are too correlated. So you're systematically under-predicting or over-predicting the value of the measurement data. If you have these systematic errors, then you have another type of problem. And here you would have that the residuals, the difference between the simulated value and the measured value, it's always the same sign, or it's too often the same time many times in a row. So to test for that, you want to use some other types of tests, which could be whiteness tests and run tests. So here we have the residuals. And if we take a whiteness test, we are simply looking at the correlations these residuals. You can also do a run test where you have the number of sign changes, and then you compensate where here this is the number of data points. So you would, if you have truly independent, you would have this many runs, so this many sign changes. So if if this is not a binomial distribution, then your assumption is not fulfilled and you have too many runs. So all of these are different tests. You don't need to understand at this point the details of these formulas. You just need to know that you can also check for the correlation of the residuals. So there are some tests that is doing that. So finally, we also want to have some tests that are comparing models. So here you're using again the log likelihood function that we encountered in the first video in the blog, and you're simply taking the difference between these two cost functions. So the logarithm of the likelihood is simply the cost function. So you're taking that difference times 2, and that should again follow a chi-square distribution. And the degrees of freedom here is the number of the difference in the number of parameters. And this builds on a number of assumptions. It builds on the assumption that the models are nested, so that all of the parameters in the smaller model appear in the bigger model. It's just that it has some additional degrees of freedom. That's the only time when you really can use this. Many people use it otherwise also, but then you're violating some of the assumptions. So here you're simply comparing the costs, and if the cost improvement is smaller than the cumulative chi-square distribution, where the degrees of freedom is the number of parameters that you added. If the improvement is smaller than that cutoff, then the addition of those degrees of freedom is not warranted. So then you should choose the simpler model, and vice versa. If it is bigger, then the new parameters are warranted. That's basically the idea here. Okay, so you see that you have these statistical tests, and you need to compare them with the distribution. And there are all sorts of assumptions involved in finding this distribution, and that's an important limitation of all statistical tests. You should always take them with a grain of salt because of that, because these assumptions are never fulfilled. There is a more assumption-free approach, which is to use bootstrapping. So you remember where you create these bootstraps and you do the tests many times for each of these bootstraps, and then you get the distribution. So you can compare your value with that. That's one way to do that, to get away from these assumptions. It's computation and much more heavy, but it's sort of more robust. You don't have to make all of these assumptions. And in this way, you can also look at combination of tests. So you can combine a run test with a chi-square test, and so on. Our analysis shows actually that the best combination, if you have two models that you want to distinguish between, is actually to use the likelihood ratio test. But you should get the distribution from a bootstrapping approach. Okay, so again, if you want to judge or compare models, statistical tests are good, but it's maybe even more important to simply use validation data. So here you have one model in the black, which is sort of doing like this, and then you have another model which is going through all of the data points. So here the cost would be very small. So here the cost of this orange model would be much, much lower than the cost of the of the black one. So it would seem that the orange one is much better. However, this is a clear example of overfitting, where new data, new validation data, would be predicted not perfectly by the previous model or by the black model, but it would sort of be as good as it is at agreeing with the training data here. Whereas the orange one, because it's so overfitted, it has fitted to all of this noise and all of these sort of variations that probably are not really there in the data. So that would be seen when you have the prediction. So it would be widely wrong in predicting new data. And this whole idea is called to use some data for estimation and some for validation. And this is a super important approach to test a model. Can it predict data that it hasn't been trained to? And all of this has to do with sort of punishing overfitting, which is that if you have the cost and you train the model to estimation data, then the more complex the model, the better it will be at agreeing to estimation data. But at some point, your ability to predict new validation data will not improve. So this is typically the sweet spot that you want to be at, where you are no longer getting better at predicting new data. You want to have the optimal prediction of validation data. So this is the place that you want to be at. This is the optimal model. And you can get to all of this if you save some data for the validation test. Okay, so yeah, and over here we have overfitted model. So that was it for this video. Now you know at least the basics of how to use this type of statistical tests to draw conclusions.